Hello everyone. In this video, I am going to show you how you can make your own IR sensor array for a line follower robot. Many of my subscribers from different countries have followed my line follower robot coding playlist, and one of the most frequently asked questions is about the sensor I used. However, the sensor module itself is not available in most local electronics shops, making it difficult for many viewers to build the same setup. To solve this problem, in this video I will use the most common electronic components that are widely available all over the world. This means you can easily collect the required parts from your local market or online stores and build the sensor array by yourself without depending on any custom-made module. If you are new to this channel, please subscribe and turn on the notification bell so you don't miss any of my upcoming videos. Now let's take a look at the components required for this project. I will attach the purchase links for each component in the video description so that you can easily find them. The main IR sensor used in this project is the TCRT5000L. First, let's understand the working principle of a TCRT IR sensor. A TCRT IR sensor consists of two main elements. The first one is the blue LED, which acts as an infrared IR transmitter, and the second one is the black-colored LED, which acts as an IR receiver. As shown in the pinout diagram, the TCRT sensor has 4 terminals. 2 terminals are used for the IR transmitter and the other 2 are used for the IR receiver. The blue IR LED continuously emits infrared rays, similar to how a normal LED emits visible light. These IR rays are directed toward the surface below the sensor. When the emitted IR rays strike a surface, they are reflected back depending on the color and brightness of that surface. The black-colored receiver LED detects these reflected IR rays. In the animation shown on the screen, you can clearly see the working principle of the IR sensor in action. An important thing to remember is that infrared light reflects well from bright or white surfaces but is largely absorbed by black surfaces. As a result, very little or no IR light is reflected from a black object. Depending on the circuit design, the microcontroller may receive a lower analog value when IR light is reflected and a higher analog value when no reflection occurs, or vice versa. However, regardless of the circuit configuration, the sensor readings obtained from black and white surfaces will always be noticeably different. This principle is widely used in line-following robot. The sensor's primary job is to distinguish between black and white surfaces, allowing the robot to detect and follow a line accurately. Before building the final sensor array, first assemble the circuit on a breadboard and test each sensor individually by monitoring its analog output values. You may notice through the camera that the blue LED appears to be glowing. This indicates that it is emitting infrared rays. Although IR light is invisible to the human eye, most camera sensors can detect it. In my particular circuit, the analog value reaches its maximum when no IR reflection is detected. When IR light is reflected from a bright object, the analog value drops to its minimum level. Once everything is working properly, we can begin assembling the circuit on a Veroboard. Start by taking a Veroboard that is 13 cm long and mark its center point at 6.5 cm. Drill 2 holes and mount the ball caster onto the Veroboard. Next, place the first 2 TCRT sensors on the board. Position them 2 holes to the left and 2 holes to the right of the center point. Continue placing the remaining sensors in the same manner, keeping a spacing of 4 holes between each sensor. Here you can see the backside view of the sensor array after soldering all the sensors. The corresponding pin mapping diagram is also displayed on the screen for reference. Begin the wiring process by connecting together the cathodes of all IR transmitter LEDs and the emitters of all IR receiver LEDs. This common connection will eventually be connected to ground. You can see the wiring arrangement on the screen. Simply follow the same pattern. Next, connect the anode of each transmitter IR LED to positive supply through a 500 ohm resistor. These resistors provide the required current to power the IR LEDs, allowing them to emit infrared rays toward the surface. Follow the circuit diagram shown on the screen and connect them exactly as demonstrated. After completing this step, join the other ends of all the 500 ohm resistors together. This common point will later be connected to the positive power supply. Now, connect the collector of each receiver LED to the positive supply line through a 4.7 kΩ resistor. This positive supply line is the same upper rail where the second terminals of all the 500 ohm resistors were connected. You can see the circuit condition on the screen after completing this step. Next, I am attaching L-shaped header pins to bring out the signal connections of all sensors. Including the 2 power connections, a total of 10 header pins are required. The signal output of each sensor is taken directly from the collector terminal of its corresponding receiver. Since there are 8 sensors in total, we will have 8 separate signal output pins. The final signal pin mapping diagram is displayed on the screen. At this point, all the wiring has been completed exactly as shown. Here is the final appearance of the sensor array from both the top and bottom side. After completing the circuit assembly, it is important to verify all connections using a multimeter. First, I check the continuity of the signal lines. Then, I measure the resistance between the positive power supply and the anode of each transmitter LED. After that, I measure the resistance between the positive supply rail and the collector of each receiver LED. As you can see, all connections are correct and the resistance values are exactly as expected. The sensor array is now fully assembled and ready for use. Now it's time to test this sensor. As soon as the sensor is powered on, all of the IR transmitter LEDs will start glowing like this. However, this light is invisible to the human eye and can only be seen through a camera. To test the sensor, I am uploading a program that reads the analog values from analog pins A0 to A7 and displays them on the serial monitor. The sensor connections and the orientation of the sensor are very important for obtaining accurate readings. Here, I have clearly demonstrated the correct sensor placement and wiring. You can also see how the sensor readings are stored sequentially inside a sensor ADC array. After uploading the code, open the serial monitor, and you will be able to see the sensor readings in real time. The values are displayed in a left-to-right sequence corresponding to the physical arrangement of the sensors. When there is no reflected light detected by the sensor, the analog reading reaches its maximum value. However, when a bright reflective object is placed in front of the sensor, the reading decreases to a minimum level. This confirms that the sensor is working exactly as expected. Now let's test the sensor on black and white surfaces. On a white surface, the sensor readings typically range between 50 and 200. To achieve the best results, the sensor must be positioned correctly above the ground surface, not too high and not too close. On a black surface, the sensor readings rise above 900. Based on these results, everything looks good, and the sensor is ready to be used in a line follower robot. Now let's talk about the advantages and disadvantages of this sensor design. One of the biggest advantages is its low cost. It uses components that are inexpensive and easily available worldwide. However, there are a few limitations. The sensor requires proper calibration, its performance can be affected by ambient light conditions, and its response speed is relatively slow. Because of these limitations, it is not the ideal choice for high-speed line follower robot. That said, this sensor is an excellent option for beginners and for anyone building a line follower robot on a limited budget. It is perfect for learning, experimentation, and general-purpose robotics projects where achieving maximum speed is not the primary goal. For those who want even better performance, you can check out my latest sensor design specifically for fast line follower robots. If you are from Bangladesh, you can directly collect it from Robotics Innovator Shop. If you are from any other country, you can still get one by contacting me, and I will do my best to help you. Thank you for watching this video all the way to the end.